Hello, and welcome to Slooh, your interface to outer space. We have a special show tonight, bringing to you live some of the astronomers from Project Blue, a mission to image what I'm going to call the first exo pale blue dot, basically an Earth like planet, and they want to look for it in our own stellar backyard. Our solar system's nearest stellar neighbor is the Alpha Centauri system. You can see in our live view from the Chile telescope. It's our wide field camera, all sky, and we're looking up at the sky now. We're focusing on the Alpha Centauri system. Unfortunately, we're dealing with some haze, so the clouds might get in our way, but we'll do our best. And this nearest neighbor to us is made up of three stars, this system, and they're Alpha Centauri A, Alpha Centauri B, and what you might be more familiar with, Proxima Centauri. So we're going to call them Alpha Cen A and Alpha Cen B. And these stars are quite like our sun, actually, whereas Proxima Centauri is much smaller than our sun. But so Alpha Cen A and B, when we say they're like our sun, what's the first thing that we think of? Aliens! I'm just kidding. But it does mean that it could be worth looking at them to see if there's a planet that might be like ours, because we're very familiar with that kind of environment in the habitable zone. For a planet to be like ours, we're talking about a planet that's in the habitable zone of its star that's about half to 1.5 times the size of Earth. This means that based on the star's size, the planet is at a safe distance away from being boiled, but close enough to not be frozen. So Earth is obviously in this safe habitable zone, and that's why we have liquid water oceans and a terrestrial home. We're also fortunate, though, that we have a magnetic field and an atmosphere and other things that keep our planet habitable, but more on that later. Since Alpha Cent A and B are similar in size to our sun, their habitable zones would be around the same distance away as ours. And for reference, our habitable zone is at 93 million miles. Proxima Centauri is the third Alpha Centauri star, but like I said, it's much smaller. It's considered an M dwarf, and it's about a tenth the size of our sun. So its habitable zone would be much closer in, where a planet would be in a safe environment temperature wise to host life. And this causes a whole nother swarm of issues for the planet. So if you were on a planet far away and you wanted to look for life somewhere out in space, there are several things that you could look for. First is that magnetic field would be a good start because it protects us from our sun's harmful radiation, along with our atmosphere, which not only tells you that life would be protected below it, but based on the chemical tracers that are in the atmosphere, you can see abundances of things like methane, which could tell you that there's life below the atmosphere. And then perhaps one of the more palatable ways to look for a planet with life would be to see if it actually looks like Earth from far away. Literally, is it blue? Back in 1990, Carl Sagan, a member of the Voyager 1's imaging team, persuaded them to turn the camera around as it was going out of our solar system to take one last look back at Earth before the spaceship left our solar system completely. He fought really hard for this, but he got his way, and the camera turned around, and we can look at an image of Voyager's pale blue dot. You can see that the Earth is a speck just less than 0.12 pixels in size, less than a tenth of a pixel. But Sagan saw much more than that little pixel. He coined the term the pale blue dot. And this blue that we see of ourselves is actually a combination of things. It's both our water, our vast oceans, and also the efficiently scattered blue light in our atmosphere that comes from the sun as the sun pours onto us. We find another pale blue dot out there, it could indicate a world much like our own. So Project Blue is on a mission to take the first picture of an Earth-like planet. Using a state-of-the-art exoplanet imaging telescope that'll be sent into low Earth orbit, they will focus specifically on the sun-like stars in the Alpha Centauri system, our closest neighbor, at just 4.37 light years away. So it's pretty close. This instrument will be equipped with advanced high-contrast imaging technologies embedded in a coronagraph, which suppresses the light from the main stars and then allows any planets around it to be seen and imaged. With an estimated launch date coming soon in 2021, Project Blue is asking for the public's help to fund their engineering and construction. So let's meet some of the team working on this exciting project. First up is Dr. Eduardo Bendek, a research scientist at the NASA Ames Bayer Institute. Welcome, Dr. Bendek.
Thank you very much, Paige. Thank you for having me here on this
We're
live
happy to
event.
have you. We were hoping to be looking more through the Slooh's telescopes tonight live, but unfortunately we're dealing with some weather, so we might not be able to see Alpha Centauri for you tonight in our scopes, but we'll try. So in the meantime, could you tell us why we're looking at the Alpha Centauri system particularly? Why is it so important to the astronomy community? Dr. Bendek, can you hear me?
Yes, I can hear you.
Okay.
So yes, Alpha Centauri is a very unique system. It's what I call a low-hanging fruit. The reason that I call it that way is because, as you mentioned before, most of the stars are brown dwarfs, and we don't know exactly how life could survive around a brown dwarf. Are stars that they present solar flares and a radiation environment that the life as we know it will struggle a lot to survive. Therefore, looking for life around sun-like stars is the logical step for us because we want to find a place that is as similar as the solar system. There's so much uncertainty on the space exploration. There are so many things that can go wrong that you do really want to minimize the adversity of the exploration. Therefore, Alpha Centauri, by being so similar to the sun, gives you a very good setting for exploring what other planets are around there and if there is any planet like the Earth. Now, the next star that is like the sun, it's 11.7 light years away. Therefore, it's almost three times farther away than Alpha Centauri. Therefore, it is clearly a lot easier to image the habitable zone of Alpha Centauri than the next sun-like star. Now, also, Alpha Centauri is a binary system. Therefore, you have two stars to look for planets, and therefore that makes the system even more compelling. Now, there's people that argue that the binary system creates or make the process of planet formation more difficult. However, I think from my point of view, from the statistics that I handle, the fact that there are two stars doesn't double completely a probability, but increases it further than having only one. So there are two competing effects. One is the fact that you have two stars, and the other competing effect is the diminishing probabilities because of having a binary system which degrades the planetary formation process. But the fact of having two stars wins, from my point of view.
That's a funny argument. I hadn't heard that.
Yeah, it's a paper that was published with a title that says the ruinous binary effect for planets. And it's about how, and it's extremely sensitive for separation. So imagine if you have the two stars very close to each other, then the gravitational field prevents from the accretion these to form and to have a quiet system where the planet can form. If the binaries are far enough apart, then each planetary system formed by itself without having too much influence. Alpha Centauri falls in the category of stars that are far enough apart. So actually the key element is if the stability limit, and we define the stability limit as the farthest that you can be at the star, that the planets are going to be gravitationally bounded to one star, is beyond the habitable zone. So anything within the habitable zone is linked to the star.
So, but we already know that there's a planet around Proxima Centauri, the third star in the system. So why aren't we looking there at that planet?
Well, the planet around Proxima b, it's around a brown dwarf. Brown dwarfs, as you mentioned before, are not very good for life in the sense that they're very unstable with a lot of radiation coming into the planet. But there is a big element here. Is Proxima b is orbiting Proxima Centauri at a very short distance to be able to receive enough heat for that star that is very cold. Therefore, the angular separation between the star and the planet is not more than 35 milliarc seconds. So 35 milliarc seconds is extremely small distance. And with current telescope, we cannot resolve that. So you cannot
Oh,
distinguish the planet from the star.
okay.
So
So
the only,
it's an observing issue as well.
as well, that,
Yeah.
so there are two things. One, the planet, we don't expect that it's going to be a place friendly for life, but also it's really hard to observe because it's too close. Even James Webb telescope, space telescope, is not going to be able to observe the system.
Wow.
Um, so you will need the next generation telescope, the extremely large telescope that are 40 meter in aperture to be able to see it.
Okay.
Um, so that's the reason that
That's
Alpha
really interesting.
Centauri, you can resolve the habitable zone of Alpha Centauri with a 30 centimeter telescope. So that makes a big difference
Hmm.
here.
Yeah, that's really interesting. So, what kind of technology would go into building a telescope that's capable then of imaging the habitable zone around Alpha Centauri?
So here you have a trade. If you're looking for planets like Proxima Centauri, which are brown dwarfs, planets around brown dwarfs, the contrast is not that big. So the star is dimmer and the planet has always the same brightness. In order to be habitable, need to receive a constant amount of heat that is similar to the Earth.
Hmm.
Therefore, as you are around a brown dwarf and a cooler star, your contrast, the difference in brightness is less. However, you're putting the planet so close to a star that you need more resolution. So you need a larger telescope, but you don't care much about the optical errors because you don't need to constrain the light of the star so precisely. Instead, if you go to Alpha Centauri, what happened is that the star is very bright. The contrast ratio between Alpha Centauri and a possible planet will be 10 billion times. Imagine you have 10 billion times contrast, and then you need to be able to suppress that light completely to see the
Right.
planet.
Right.
Now, in the case of Alpha Cen, the planet is at zero point 0.7 arc seconds away. So it's much farther. Therefore, you don't need a big telescope. You can do it with a small telescope, but the telescope has to be extremely precise because you have to control the light of the star so well that any tiny bump on the optics will flood the field of view with light. So answering your question about technology, there are two elements. One is the coronagraph, which is basically a device that removes the diffraction rings because any telescope, it creates diffraction ring around a point source. Those diffraction ring will be on top of the planet and will be way too bright than the planet, and therefore you cannot see them. So first you use a coronagraph that remove those rings, and then you have residual imperfections on the optics. And for that, you can use a deformable mirror. So a deformable mirror is a device that you can modify the shape in orbit of the mirror to compensate
Ah,
for other errors on the system.
okay. And for our viewers, we're looking at images of the Alpha Centauri system, and we were just flipping through a couple that we bring it up right now that actually some of our members took back in 2010. So this is the Alpha Centauri system, and what Dr. Bendick was just talking about, this bright light that we need to block out in order to be able to see what's close in to the star. You're looking at it right now, so that's the light that we need to block out using the coronagraph and the diffraction grading that we're talking about is coming from this light. So being able to, you basically effectively, like, you put, like, kind of, if you put your hand over it almost even, whereas so then you could see around it. That's the kind of technology that we're talking about here. This is a cool image that was taken. This is from the Slooh telescopes, are one of our wide fields. But so one of the things our viewers are probably thinking, because I know that I was for a while too, is okay, so if we find a planet in the habitable zone around Alpha Centauri, this star is the closest one at only 4 parsecs away, which, like you said, is like really great. It's not that far. Could we go? Can we travel that far?
Well, that's a great question, and I love those questions where we touch uh, reality and science fiction at the same time because it's something that we don't know exactly how to do it, but it's not impossible. So it really triggers um, research, investigation, and imagination, which is what moves society forward. Um, as of now, we don't have a way to go there. Uh, However, there is a group, a private group called Breakthrough Initiatives that
Mhm.
is developing a system to send microships, micro spacecraft to Alpha Centauri at 20% the speed of light. Sounds like
Wow.
impossible, but they're doing a fairly good study, and they want to put a giant laser on the ground to be able to propel this spacecraft with
That's
radiation
cool.
pressure to 20% the speed of light. And actually, they are planning to install their giant laser in Chile because you need to have direct line of sight to Alpha Centauri, and you don't have that access on the northern hemisphere.
Right.
Also, you need a very good clear skies and high mountains, so it's all the same ingredients. Why the observatories to observe, to receive the photons are there. It's the same situation that you need to launch photons. So their plan is to have these microships that are like 3-gram spacecraft orbiting around the Earth, low Earth orbit. They will deploy a sail, a 4-meter sail, and then when the spacecraft goes in front of the Alpha Centauri, then they launch a super powerful laser and accelerate the device for around 2 minutes to reach 20% of the speed of light, and then you can get in Alpha Centauri in 20 years. Now,
Wow.
if you ask if you ask me, is this impossible? No. Is this extremely hard? Yes. So I think it's very challenging, but I think that somebody has to start with it. And there
Yeah.
is a very important people working on it, millionaires here in the Bay Area, and also Stephen Hawking is involved in this project. So I think that there is a kind of leap forward that we need to give
Yeah.
and to go for it. So I really support what they're doing. It's true that it's a little bit challenging, but well, it's a hope.
Right. So if it, by the time it's developed and launched, and then it's a 20-year mission to get there. So for any of you viewers watching whose newborn children might be little scientists, you can count on them having grad school projects probably in about 25 or 30 years. But
Yeah,
anyway, so I guess we won't be employing any interstellar travel agents anytime soon either. But we're gonna
exactly.
have a we're going to have a quick break. And after our quick break is Dr. Adam Frank, a theoretical physicist and professor at the University of Rochester, to tell us about some of the social impacts of the Project Blue mission. So, Dr. Edward Bendeck, we just want to thank you so much for joining us. It was a pleasure to talk to you. Thanks for teaching us so much.
Thank you, Paige. Bye.
Bye. Stay tuned. We'll be right back.
Thank you.
Slooh, your interface to outer space. We monitor and broadcast exciting developments from the Space Situation Room so you can witness the most amazing celestial moments with expert guests sharing their visions of the sky. Let us take you to worlds beyond our own.
And we're back. We're here talking about the Project Blue mission to capture the first image of a habitable world around an Alpha Centauri star. We're here with Dr. Adam Frank, a theoretical astrophysicist at the University of Rochester, who works on hydrodynamics of planetary nebulae, circumstellar disks, planet formation. He's also a well known popularizer of science with regular guest spots on NPR and their Cosmos and Culture blog. So, welcome, Dr. Frank. It's nice to have you.
It's great to be here.
So, we want to chat with you a little bit about the social impacts that Project Blue might have on our society and why people like our viewers might be interested in getting involved in something like this. So, my first question, though, really is more back to the basic bones of this is, Kepler has found a few thousand exoplanets just alone. And then, we have other ways of detecting exoplanets as well. We know that there might be two worlds in the habitable zone around the TRAPPIST system that's been in the news recently. Why haven't we been able to see blue before? Why haven't we seen an Earth-like world?
Well, I mean, when we think about exoplanets, also we need to remember that even 20 years ago, 21 years ago or so, this question was unanswered about whether or not there were any other planets. The question about whether or not there are other worlds orbiting other stars goes back to the Greeks. It's a 3,000-year-old question, and it gets answered in our lifetimes, or the lifetime of some of your viewers. So first of all, you have to recognize no matter where we are miles away from the kind of, in some sense, complete ignorance that we had about planets even a couple
That's true.
The transition that happened over the last few years was really really via Kepler more than anything else. So the RV searches, the radial velocity searches, mattered a lot because they were the first ones to find it. But all of these searches, what they basically allowed us to tell was where the planet was and the size of the planet. But that's it, right? Only recently have we been able to do, just beginning to be able to catch some of the light when we do transits that passes through the atmosphere, this tiny limb of an atmosphere, and begin trying to characterize those atmospheres. So that's as far as we've gotten. So even though we've found planets in the habitable zone, we've found planets that we think are the right size, that's as far as we've gotten. So when it comes to things like characterizing the atmosphere, characterizing the colors of the planet, that is the frontier, and that's why this project is so important. So it's a long multi-step process to get us to the ultimate question, right? Our ultimate question is about life. We already have made huge leaps, but there's still, this Project Blue is sort of the next step to start getting spectral information, start looking across colors, being able to image directly, because that has not happened. We have never, or certainly Earth-like planet, we have not been able to image. We've been getting information about the planet indirectly through the transits, through the radial velocity. So actually directly imaging and getting some spectral information, some colors, that's totally new.
Right. That's so cool. It's crazy to think that not that long ago, we didn't even know that there were planets around other stars and how far we've come. We have over 3,000 detected planets already, and that's just recent. That's within the last decade, and that's so cool. Finding life on other planets, I mean, even before we knew about exoplanets, but especially since it's been so sensationalized in the media, it's just a constant barrage of, is there aliens? Is there life? But I want to share with our viewers a quick quote from Carl Sagan, who coined the term we mentioned, pale blue dot, from the Voyager 1 image. And he wrote a book called Pale Blue Dot. And the quote is quick. I just want to share it with our viewers. It says, "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was lived out their lives. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world." And you can see this in this image. We mentioned earlier that that speck was less than a pixel in size when they took this image. And so that's from Carl Sagan's book. But what real impacts to science and society do astronomers think that finding another pale blue dot would have? We just heard from Dr. Bendeck that if we even find one around Alpha Centauri, which is our closest chance in distance-wise, we can't go there. So what kind of impacts do you think we would experience in the short term from this?
Well, I mean, it depends on what we think about when we think about impact. So finding a pale blue dot, again, is just a step in the direction of finding about whether or not there are other biospheres, right? And finding other biospheres is the step towards finding whether or not there's any other civilizations. Are we the only species in the history of cosmic evolution that has looked back on itself and asked why and what, finding a pale blue dot alone would be magnificent, but it would still be a step before. It's still not quite the final step in terms of significance. When we ask about whether we go there or not, we have to understand that there's a transition that's happening on Earth right now. So I just finished a book called Light of the Stars, Alien Worlds, and the Fate of the Earth, where what I was working on, I've done research, I have this research project on this, is the idea that right now we're going through this very interesting period in the biosphere of climate change, right? Human beings have pushed on the climate because of their activity. And now the climate is shifting away from the state that we found it in when we were, when civilization began. And really, what this is a particular strange moment that actually amazingly ties into exactly what the looking for pale blue dots about and looking for other life is about, is that we need to recognize that unless the universe is very biased against evolving civilizations, that this has happened before. So this is a paper I wrote with Woody Sullivan a couple of years ago, that unless the universe is extremely, the probabilities are extremely arrayed against it, then over the course of cosmic space and time, other places have evolved civilizations. And if they've evolved other civilizations, then what we're going through with climate change is probably not unique. And that's just because, you can't build a world-girdling civilization without pushing back on the planet. It's just sort of like the second law of thermodynamics, essentially. So this march we're making upward in first discovering planets, and now we know that every star in the sky has planets. Every star in the sky has planets, and that's why we can make the claims that we make about the universe having to be so biased against exo-civilizations, or else we're not the first time it's happened. So this ladder we're climbing up of is really, in some sense, teaching us about ourselves. Climate change, issues of sustainability, what's called the Anthropocene, that this new era that we've pushed the Earth into, where human effects are really becoming the dominant forcings on the Earth systems, oceans, atmospheres, etc. That what it is, this is the end of our childhood. This is childhood's end. To quote a science fiction story by Arthur C. Clarke, we're waking up to what we are and what our place is on the planet by seeing other planets, right? By learning about Mars and about Venus and about climate on those planets, by learning, by doing the work to understand climates on something like an M-dwarf world. We are also taking our understanding that we've gained from Earth and applying it to ourselves to understand what our future might be. So I think in some ways this is about our maturing as a sort of cosmic civilization, because pretty much we're at the point where when you're a teenager, right, you get the keys to the car, and either you learn how to deal with it, right, or you don't. And right now we've sort of been given the keys to the planet, and the question is whether we drive it off a cliff or not. And probably other civilizations have been in this position before. It's probably not the first time. And like I said, this is, I think the real significance of this is our waking up to the reality of life and planets and their shared fates.
That's a really interesting perspective, because when we think about finding life on other planets, we know that the chances of it looking like us are really, really slim. And we're specifically even just looking for microorganisms. But being able to maybe see a planet in different phases of its habitability evolution. So whether life is just starting or whether life is past because they drove their planet off the cliff, like we might do. That would be really interesting.
Go ahead. Sorry.
No, yeah,
well, I just
go
think
ahead.
that the whether or not we'll find evidence of an exo-civilization is something. I mean, this is even for SETI, right, which is the search for extraterrestrial intelligence. That's changed. We're in a new era of that as well, because it used to be that, like, oh, you had to take a radio telescope and then you had to figure out which stars to look at, and it was this whole sort of like, if they know that I know that they know that I know that they know that they're going to send a signal, then so it was like traditional SETI, there was just so many assumptions built in. But now we're just going to be staring at planets. We're going to spend the next 50 years staring hard at planets. And we already saw what happened with the WTF star, right? The star with the crazy fluxes, the Kepler star. Now, of course, odds are that has nothing to do with an alien megastructure. But, we're going to be staring at planets. We have to be prepared to see interesting things.
Absolutely.
So we're just entering a new era. We're entering a new era in thinking about life and planets. And that is what impacts us, because what is happening to us now, like whether or not civilization as we know it is able to make it for another 200-300 years, is really dependent upon us figuring out how to deal with ourselves as a dominant form of life on this planet.
Yeah. And we are also continuing kind of on that same topic of thought, the era of technology being motivated by science and vice versa. We have a lot of technology that came from NASA, that came from planned space missions, things that are used every day in the military. We see this with like Elon Musk and, Tesla versus SpaceX and all of those things. And so even if we don't find a planet, it's interesting to think that a space mission, and particularly Project Blue, could have impacts on technology too. Even if we don't turn up a blue planet, you still forwarded science in a really amazing way.
Yeah, well, I mean, this has been the whole history of blue sky, what they call blue sky science, right? People say like, oh, why are we giving money to do space missions? What is that going to give us? And I always like to remind people of this little thing called an internet browser. The first internet browser was developed in an astronomy laboratory. for moving data back and forth. Mosaic was the first. Now, let's see, were there any applications of that? Did anybody make any money from that? I don't know. I'm not sure. So like, and the list just goes on and on and on. I mean, really, the world we live in now, this crazy high-tech world where there is, this remarkably short distance between a new technology developed in a laboratory and the new product you have in your, in your pocket. That is intimately tied with the research and development effort that is federally funded, and in particular, the research and development effort that is about space. We're poised right now to be putting in these micro, or the CubeSats, these small satellites that are going to give continual pictures of the Earth 24 hours a day. Now, whether you like that or not, I don't know, but there's huge business opportunities in that, from farming, agriculture, mining, you name it. And so, would that have been possible without the kinds of things that, the astronomy and space science? No, not at all. So no matter what we do with this, having to solve these very, very difficult technical challenges always ends up having fruits for the rest of society.
Yeah, absolutely. That's enough motivation for me, at least. That's why I dedicated my life to it. I guess that's why we all did.
We all did. Right.
All right, Dr. Frank. Well, thank you so much for joining us. It was great to learn from you.
We're going to have one last.
Awesome. We're going to have one last quick break, and then we'll be back with our final guest of the evening, Dr. John Morse, the CEO of Project Blue. And he'll be telling us all about the project's timeline, funding, and what you can do to get involved. So stay tuned.
Bye.
Slooh, your interface to outer space. Here, you'll find a vibrant global community of fellow Earthlings together searching for what's out there, controlling high-powered telescopes on missions to see and understand all that lies beyond our planet. So gather with us around the looking glass.
Thank you for taking the time.
Hi, we're back. We're here with Dr. John Morse, the CEO of Project Blue, a mission to capture the first image of a habitable world around an Alpha Centauri star. Welcome, Dr. Morse.
Great to be here. How are you?
Good. How are you? We're so
doing
excited.
Great. So did the sky clear up at all down in Chile?
Unfortunately not.
No.
Unfortunately, I think it's gotten even worse. Yeah. But what we are looking at here is an image that Project Blue is anticipating that the pale blue dot that would be around an Alpha Centauri star would look like. So this is really crazy to think about the Voyager 1 image that we saw earlier in the show, which was, I keep saying, but a tenth of the size of a pixel. And then this image here, which is just incredible. And this also shows that coronagraphic method that Dr. Van Dijk told us about earlier, where we block out the light from the stars so you can see the planet. But this is just super cool to look at.
Yes, this is a nice simulation. We hope to do more simulations like this by Professor Jared Males down at University of Arizona, who's involved on Project Blue. And he's trying to simulate the performance of the telescope. And this simulation that you're looking at is, what if we were looking at Alpha Centauri A and trying to see the planets in our solar system? And so the one on the upper right is Venus, kind of whitish. And the one on the left is a pale blue dot Earth. Now, there's lots of pixels in those little pale blue dots, but that's just a function of the how the detector is sampling the image. We won't see any details. It will definitely be a pale blue dot, unresolved, but we hope to be able to capture images in at least two colors, one in blue and one in green, and possibly another one in yellow-red, so that we can see whether it has a blue hue, which would be indicative of the oceans and the atmosphere, as you were talking about at the top of the show.
This is so exciting. I'm a bit biased for my support of this project, because this is the core of my personal research. I study low mass brown dwarf and exoplanet atmospheres, and this is would be incredible if we actually saw something. But just to know that it's so close to Earth is really neat. But let's talk about how Project Blue is being supported. And so the way they're going about securing the first phase of funding is really unique, and it's a new way of doing things in the science and public community. Why is the time right now ripe for pursuing privately funded space science missions?
There's a couple things going on right now. One is that there's so much energy in space exploration with new companies. You already mentioned SpaceX, but Blue Origin
Hmm.
and this emergence of the small satellite market, which is doing amazing things and very rapidly, developing new launchers, developing new kinds of cameras, mostly for Earth observing, and new kinds of capabilities. And we want to take advantage of all those developments in order to bring the cost of our mission down considerably compared to what it was just 3 or 4 years ago. And then, in addition, there are resources going into private research, could be medical research or even ground based telescopes like the Keck telescopes or the Magellan telescopes, which are privately funded. And the scale of the mission we're talking about is tens of millions, but that's about of dollars, but that's about
Hmm.
the scale of a pretty sizable ground-based telescope project. And there are people who are funding those projects. And so we think that by pursuing really exciting, high-impact science goals, that it's possible to privately fund these. It could be through philanthropy, which is how a lot of the basic research is done. But we also want to look at the idea of doing maybe science prizes in the future, where, like the Google Lunar X Prize, is holding out a cash reward basically for companies that land on the moon and perform some basic tasks. We would like to look at having those kinds of prizes, either supported by the government or major research foundations or together, and look at very daunting but high impact science goals that would turn loose all the innovation that exists out there in the community of scientists and technologists and engineers at universities and at companies so that we can pursue some of these goals and try to do it in a non traditional way. And that's because in my background, I used to be the director of astrophysics at NASA headquarters from 2007 to 2011. And that's when we launched the Fermi Gamma Ray Space Telescope and Kepler in
Hmm.
2009, and the last subversing mission to Hubble and the WISE spacecraft, et cetera. And there's no question that the rate of the missions that we launch is restricted by the amount of funding available. And so, what we're trying to do at Boldly Go Institute, which is where I'm CEO, and the Project Blue mission is one of those projects that we're pursuing along with our partners at Mission Centaur and the SETI Institute and UMass Lowell and faculty from several other universities. We believe we can bring together innovation and non governmental sources of funding in order to do these kinds of missions, that they're within reach. It used to be that space missions were just way too expensive, but
Right.
now we can actually contemplate them being within the realm of uh, philanthropic giving, even.
So what specific parts of this project make it plausibly fundable by
Right.
public funding and cheaper compared to a small government-led mission?
So we believe that there's efficiencies we can pursue that would make it cheaper than the normal way that the government develops the missions. However, the big change here with Project Blue is just the idea of pursuing something that has a very sharp and focused kind of binary yes or no answer. Are there planets around Alpha
Right.
Centauri? Um, Usually, when a space telescope is developed to look at exoplanets, people talk about doing dozens of stars so that they can get a statistical sample of possible planets. And people want to know that if there's a null result, if no planets are discovered, is that meaningful statistically? Is it going to teach us something about exoplanets? Well, if you're just looking at Alpha Centauri system, that null result is probably more philosophical
Hmm.
than it is teaching us about exoplanets and how common they are. And the philosophical part is just whether there's could be the first destination we go if humankind ever travels to the stars. And if there are no Earth-type exoplanets in the habitable zones of Alpha Centauri A and B, you might have to look, as Dr. Bendick said, much further away from the sun before we get to the first Earth-type planet. So with Project Blue, all missions are funded in a design phase at the beginning, which is less expensive than the construction phase, which is later.
Sure.
And we can plausibly raise on crowdfunding site. We have, for example, our Indiegogo crowdfunding campaign going on right now for Project Blue. You just go to blueigg.org, and that'll take you to the Indiegogo site. And this is an opportunity to raise funds to do that initial phase A type study, which is the initial engineering you do for the spacecraft. It is reachable with crowdfunding.
Right.
And then, in addition, we as a team on Project Blue, we really want to involve the curious public that's your audience out there right now, space enthusiasts who love astronomy, who love this idea of searching for life beyond Earth. And we want to involve you in the mission as soon as possible, right from the beginning. Now, we know we have a lot more fundraising to do. We're doing that in parallel right now, and we'll continue to do it in the future. But we're getting a start right now with this crowdfunding campaign, and you're invited to join us.
That is so awesome. That reminds me of the Kickstarter campaign that they had for the Tabby star observation time, and that was super successful. The public went wild over it. This star that has a weird like light spectrum.
Sure.
And they wanted the observing time, and they couldn't get it government based, and so they were like, well, we'll fund it ourselves, and they sure did. And it was just so successful that I have no doubt that your mission will also be incredibly successful in its fundraising campaigns. That's
Thank
really
you so much.
inspiring.
That is
Thank
exactly
you.
the kind of energy we're talking about.
Well, I think we have a good fan base that is also going to be really interested in following along with your story, and we're excited at Slooh to be a part of it and to be able to watch as you guys succeed and go forward. And I mean, it's really not that long until the mission would launch, so we're talking 5 years or less until we're getting results, hopefully. So fingers crossed, and we'll be here waiting.
That's what we're hoping. Yes.
Thank you, Dr. Morris. It was great to have you sharing with us tonight. We're really excited for the success of this, and we look forward to keeping in touch. Thank you for joining us.
Okay, great. Happy to be here.
So that's Project Blue in a nutshell, or Project Blue in a space capsule, maybe is more appropriate to say it that way. If you want to get ahead of their game, you can use our telescopes in Chile to take images of the Alpha Centauri system. Unfortunately, you won't get to see a pale blue dot because you need a coronagraph, like they were mentioning, up in low Earth orbit to even try. But you can still take really awesome pictures like the ones we're showcasing up here tonight and update our 8-year-old images. That would be great. So in the next few weeks, we're going to be live streaming the Orionids meteor shower. The night before Halloween, we're going to do a show about spooky space monsters. Don't forget, check out our telescopes every night. We have live feeds from Chile and the Canary Islands. Snap your pictures, share them in your gallery, and share your thoughts on Slooh.com. Snap a picture of the Alpha Centauri system from Chile in the Southern Hemisphere and share your thoughts about it. And if you're excited for this Project Blue mission and what you think will come of it, we're looking forward to hearing from you and to reading your posts. That's all for tonight. Thank you for joining us to hear about the Project Blue mission to see blue. I'm Dr. Paige Godfrey, and you've been watching Slooh, your interface to outer space.